All right, this video is designed to walk you through the solutions to the handout from class involving the Euclidean algorithm, Euclidean tables, and the Euler phi function. I'm hoping in the next couple of days to come up with a means of doing this with a whiteboard in my house, but we're not quite there yet. So I'm going to do this in Mathematica. And I apologize in advance. My neighbor has decided to mow his lawn while I am doing this, so you might hear a lawnmower in the background, and I apologize. My plan is to go through each problem. I will show you the work that you would need to do. I have also written a Mathematica command that will give a nice, succinct version of things like the Euclidean algorithm. It's automated. It's not in the MCP, and I'm only doing that just so you can see what it looks like when all is said and done. Okay, so with that done, let's go through. All right, so for our first values, we need to find the GCD of 25 and 90 using the Euclidean algorithm. So we are going to go with successive division by remainder. So I'm going to take 90 and I'm going to divide it by 25 and get my remainder. So how many times 90 goes into 25? Or sorry, 25 goes into 90. Goes in at least 3 times. So if I work that out, I get a remainder of 15. Okay, so now I am going to take 25 and divide that by 15. Not surprisingly, it goes in 1 and change. So I'm going to take that and I subtract 15 and I'm left with 10. All right, now I will divide 15 by 10. And again, not surprisingly, it goes in 1 time and change. So I take 15 and I subtract 10, and I get 5. 5 divides 10, and there is no remainder. So that means our GCD is going to be 5. All right, now, as I said, to make that look a little neater, I have this command. And it shows you what I computed. I took 90, I divided it by 25. I found that it went in 3 times, subtracted that to get the remainder. I then took I took 25, divided it by 15, subtracted that to get the remainder of 10, took 15, divided it by 10, subtracted that, and got a remainder of 5. So, as I said, here, the GCD of 25 and 90 is 5. The instructions on the worksheet said whenever they are relatively prime to work out the inverse. These are not relatively prime, so there is no inverse, and we are done. All right, now we will do the same thing for 570 and 918. So again, I will divide 918 by 570 to find out how many times it goes in. It goes in once. I need the remainder. All right, I paused there for a moment because the phone rang and I'm going to basically restart. So, okay, so let's go through. So we're going to find the GCD of 570 and 918 using the Euclidean algorithm. So again, I'm going to divide 918 by 570. Okay, so it goes in 1.6 times. So I need to know my remainder. And my remainder is 348. All right, as with everything with the Euclidean algorithm, again, it's just lather, rinse, and repeat. I am going to now take 570, divide it by 348. Again, 1 and change, so I find my remainder, 222. So now I take 348, I divide it by 222. Get, again, 1 and change, so my quotient is 1, so I'm taking 348 minus 222. It's 126. All right, so my new remainder is 126. I divide 222 by 126. Again, quotient of 1, so 222 minus 126. We get 96. All right. And well, we just keep going. All right, that gets us 30. Now I take 96 and I divide it by 30. You get 3.2. So now I'm going to take 96 minus 3 times 30. Gets me 6. So then I would divide 30 by 6, but 6 divides 30. So there's my GCD. If I do that last division, I'll get a remainder of 0. So the GCD of, I've forgotten what numbers we started with, disappeared off the top of the screen, 348 and 222 is 6. Okay, now so just to sort of show that in a more compact fashion, there we go. So we got the exact same set of remainders as we did before, and we end up with a 6 at the end, and so that is our GCD. All right, now so now we are going to do the GCD of 27 and 50. All right, so again, I divide 50 by 27, goes in once, so I take 50 and I subtract 27 and I get 23. Now, I'm going to make a note here because I will need it later. The quotient is 1. And quotient is spelled with an N. All right, and so then I get a remainder of 23. So now I will take 27 and I'll divide it by 23. And not surprisingly, again, the quotient is 1. So I'm going to make a note of that. All right, so I take 27, I subtract 23, and I get 4. All right, and so now I take 23, I divide it by 4. That's going to give me a quotient of 5. All right, and so then I take 23 minus 4 times 5. That gets me 3. I take 4, I divide it by 3, I get 1. All right, and then I work out the oh so hard sum of 4 minus 3, and I get 1. Okay, so the GCD of our two numbers of 27 and 50 is 1. Okay, now again, just to make that look pretty, there is the Euclidean algorithm all worked out. Again, we divided by 27, we got a remainder of 23, divided by 23, got a remainder of 4, divided by 4, got a remainder of 3, divided by 3, got a remainder of 1. So now we can complete our Euclidean table. All right, so now we need to make the Euclidean table. I've used Mathematica to generate sort of an array so I can put the values in. You can just draw it, it's fine. All right, but as always, the first two entries in the second row are 0 and 1, and these are empty. All right, I have just made it generate 10 columns. I am not going to use all of them. I didn't want to make it special. All right, so now I'm going to take each one of the quotient values, starting with the last one and working my way to the first one. Okay, so now I complete my second row. I do that by multiplying this number times that number and then add that number. So 1 times 1 plus 0, that is 1. And now I lather, rinse, and repeat. 5 times 1 is 5, plus 1 is 6. 6 plus 1 is 7. 7 plus 6 is 13. All right. Now, with my table complete, I take the last two numbers. I take 13, I multiply it by 27, and I subtract 7 times 50. That should be plus or minus 1. It's 1. Great. So that means when I reduce mod 50, this term would drop out and 13 times 27 would be 1. So what we are seeing is that 27 inverse is 13 mod 50. All right, well, let's continue. Okay, so now we're going to do 27 and 185. But by now, hopefully the procedure is looking familiar. I will divide by 27, and I get that. I'm just going to make a note of the quotient. If you're wondering why I'm using this asterisk and parenthesis, it's so that Mathematica doesn't try to make a computation in the middle of the cell. It treats it as a comment. All right, so then I need my remainder. And I get 23. All right, so now I take 27 and I divide it by 23. And not surprisingly, I get a quotient of 1. All right, so I take 27, I subtract 23, I get 4. All right, and then I'm going to take 23 divided by 4. We ran into these precise computations in an earlier problem. Q, where did Q go? Q equals 1, 5. All right, so I take 23 and I subtract 4 times 5, gives me a remainder of 3. And then I get one last quotient of 1. And again, just for sake of thoroughness, we figure out the remainder and we get 1. All right, so the GCD of 27 and 185 is 1. All right, and again, just to make it a little neater to look at. All right, but again, it's that same pattern of quotients and remainders. All right, so now, since it has a GCD of 1, I can try and find my inverse. All right, so I'm going to construct my table. Those ones are always blank. This is always a 0. This is always a 1. And then I'm going to go with my quotients in reverse order. All right, and now again, I fill in my second row, this times this plus that. So 1 times 1 plus 0 is 1. 5 times 1 plus 1 is 6. 6 plus 1 is 7. And then 6 times 7 is 42 plus 6, 48. All right. Now I do the same thing again. I take the number I'm trying to invert and I multiply it by the last number in the second row, and then I subtract 7 times the modulus. And that should always be plus or minus 1. And it's 1. Okay, so that tells us that 27 inverse is 48 mod 185. Okay, so let's continue on. We will take $719 divided by 125, and this gives me a quotient of 5. All right, so 719 minus 5 times 125 is 94. Okay, so I'm going to take that and divide it into 125, and I get 1.3. So my quotient is 1. All right, so to find my new remainder, I take 125 and subtract 94. All right, then I'm going to take 94 and divide it by 31, which is going to go in 3 times and change. All right, so I get a quotient of 3. And then I take 94 and I subtract 3 times 31, and I get 1. So again, not surprising, we find that the GCD of 94, that didn't work, there we go, GCD of 125 and 719 is 1. Okay, and again, just to make it look pretty, we get that. All right, so I can work out my Euclidean table. So always starts the same. Then I take 3, 1, 5. Those are my quotients, starting with the last one. And then again, 3 times 1 plus 0, that's 3. 1 times 3 plus 1, that's 4. 5 times 4 is 20, plus 3 is 23. All right, and now the computation. I take 23, the largest value, times the number I'm trying to invert, minus 4 times 719, -1. Okay, so this is what I warned everybody about with the Euclidean table. It works some of the time, about half. So we've got -1. So that means that 23 inverse, or sorry, 125 inverse, not 23, is -23 mod 719. All right, which is the same as 719 minus 23, which, when you work that out, is 696. All right, and just to double check with Mathematica, if we want the inverse, 696. Great. All right, one last one. All right, now we're looking at 1235 and 2578, but the numbers don't change the procedure. I just start working on quotients. All right, so that goes in twice. right, so I need my remainder. Get a remainder of 108. All right, so now I'm going to take 1235 and I am going to divide it by 108. That goes in 11 times. I'll make a note of that. And again, to find my remainder, subtract that off, I get 47. All right, and now I'm going to take 108 and divide it by that. All right, and that's going to have a quotient of 2. So it's going to be 14. All right, I take 47 divided by 14. Should go in, yep, 3 times. So I get a quotient of 3. That gives me 5. All right, and then I divide that by 5. Doesn't go in quite 3 times, so I get a quotient of 2. All right. That gets me 4. And now I divide 5 by 4. And what do you know? I get a quotient of 1. And when I subtract 5 minus 4, I get 1. Okay, so that's telling us that the GCD of 1235 and 2578 is 1. So 1235 is invertible mod 2578. All right, once again, that just, as I said, it makes it look pretty so it's easy to follow on the screen. All right, so now I should be able to find my inverse. I am going to start my first row, 2 blank cells, and then I take the quotients in reverse order. This always starts 0, 1. Let's see how good I am at my mental arithmetic while I'm typing, recording, etc. So 1 times 1 plus 0 is going to be 1. 2 times 1 will be 2 plus 1, that will be 3. And I'm going to get 9 plus 1, that'll be 10. 20 plus 3, that's 23. And now I need to know what 11 times 23 is, and that's when I stop trying to even pretend. I get 253. Whoops. Not 253. I need 11 times 23, which is 253, but then 253 plus 10. That'll be 263. All right, and then we will take 2 times 263 and we will add 23 to it, and that is going to be 549. All right, now I made an arithmetic error. I almost added the wrong number in when I was doing this one. So I am going to pause this video for a moment and double check my answers before I do the computation. All right, so I have double checked my work and it is indeed correct. All right, so to work this out, now again, I'm going to check. I'm going to take 1235, I multiply it by the last number in the second row, and then I subtract 263 times 2578, and I get 1. Beautiful. So I don't have any more work to do. That means that 1235 inverse is equal to 549 mod 2578. All right, this video is now approaching 25 minutes long, so I am going to stop there, and I will do the solutions to the Euler phi in a separate video.